So in this video we will discuss two important instructions in arithmetic operations called DAD, DAD, RP, and DAA. These two instructions. So let's look at the first instructions, DAD RP. So this DAD RP means that this is double accumulator resistor. So in this instruction, the resistor provided is of extended pair. So for example, let's take an example, DAD V. So what does this instruction do? This instruction, this P is in extended form, resistor pair. So we will take VC, and then we will take HL. So the content of BC means the resistor pair which is provided in the instruction will be added to the content of HL pair, and the result stored again in the HL pair. Okay, this is how this DAD instruction works. And we have very important instruction called DAA, and it is followed by nothing else. So it is an implied instruction, implied in the sense that it doesn't followed by any operand. And by saying DAA, we know that the content of the accumulator after doing some BCD operations, that accumulator should be adjusted. Okay, before going to this DAA instruction, let's look at some of the important foundations. Okay, let's see what hexadecimal numbers are. So in hexadecimal number, hexadecimal by the name itself, hexadecimal number has a base of 16 from 0 up to 9, and then after 9 we have A up to F. Okay, this hexadecimal number can be represented by binary using 4 bits. Okay, so this hexadecimal 0 will be represented in binary by 0 0 0 0. This 1 will be represented by 0 0 0 1. 2 will be represented by 0 0 1 0. Likewise, we can represent 9 as 1 0 0 1, this A as 1 0 1 0, and this F as 1 1 1 1. So this is a binary representation of hexadecimal number. Okay, and we have another concept called BCD. BCD means binary coded decimal. So in BCD, every decimal number, we can have decimal numbers from 0 1 2 up to 9. 9 is the greatest BCD number. Okay, so in BCD, every digit in decimal from 0 to 9 is represented by binary numbers like this. Okay, so this is 0 0 0 0 H. This should be followed by H, 0 0 0 1 H, up to 1 0 0 1. And in BCD, For this binary itself, we can extend like 1010 1011, okay, and then up to this is 9 10 11 12 means 1100 12. 13 means 4, okay, 14 means 14 8 and 4 and 2, okay, 1110. 15 means 1111. In the binary representation, these numbers can be possible, okay, these numbers are possible, but in BCD, in binary coded decimals, this number represents any this binary numbers doesn't represent any uh, doesn't correspond to any decimal number. So these numbers are called invalid, okay, these numbers are invalid in BCD. So these numbers are invalid and it cannot be happen using BCD operations. Okay, let's take an example. Let's take an example that let's take an example, and what we have to know is that this DAD instructions, okay, not DAD, this DAA instructions is used specifically for uh, binary, not binary, uh, BCD BCD number uh, adjustment. Okay, this DAA instruction is specifically used to adjust uh, BCD BCD. Okay, so let's take an example. Say let's try to add two numbers. Okay, let me, okay, let's try to add two numbers. Uh, say for example 4 7H and 3 5H. Okay, these two numbers are BCD. Whether this is BCD or hexadecimal, it depends on your interpretation. Okay, so let's think that these two numbers are so let's first represent these two numbers in binary. So for 4 we have 0 1 0 0, 7 0 1 1 1, 3 0 0 1 1, 5 5 means 0 1 0 1. So if we add these two numbers, what is the result? This is 0 1 carry 1 1 0 1 carry 1 1 0 and then 1 1 and then there's 1 carry. Okay, okay, and there's 1 carry. Okay, is it right? Let's check. 1 1 1 1 0 1 carry 1 1 0 1 carry 1 1 0 and then 1 1 1 carry. Okay, and then for this we have 0 1 1 0 1 1 1 0. Okay, if you represent these numbers in hexadecimal, we have this 8 and 4, this is 12, so this lower level has an equivalent of 12. Okay, So this is composed of two digits, not one digit. Okay, and this number is in invalid number range. Okay, so what should we do for this kind of situation? Like in BCD addition, if the lower nibble is the lower nibble corresponds to a number which is beyond the BCD number range. So in this kind of situation, we have to get rid of these invalid numbers. Okay, in BCD numbers we cannot have these numbers. So by mistake in BCD addition, by mistake, if the answer or if the result falls into this range, what we have to do is that we have to get rid of the 6 numbers. How? We can add 6 so that it get rid of these numbers. So in the same situation here, the answer, the sum of this lower nibble is 1 to 12, which is not a digit in decimal. So to get rid of these situations, we have to add 6, which is the number of invalid digits, and then let's see what happens. If we add 6, 0, 1, 1, 0. Okay, we can add this. So this is 0, 0, 1, 1, 1, 1. 1, 1 means 0, 1 carry, 1, 1, 0. And in this situation, there's a carry from this bit number 3 to bit number 4. Okay, and this is a situation where that our auxiliary carry flag is set. Okay, so 1, 1, 1 with the carry, 1, 0, right, 0, and then 1, 0, 1. Okay, 1, 0, 1. Okay, so let's again see the situation. Okay, let's again see the situation. What is the result? This is 2, this is 8. Okay, so in these situations, what we get is a valid BCD. Okay, valid BCD number. So this is how this DAA instructions adjust the numbers in BCD. Okay, and if, say for example, by adjusting lower bit, if our upper bits become invalid, we will do the same by adding 6 means 0, 1, 1, 0 to the upper nibble, and we have to do the same. Okay, and this is how this DAA instruction works. Okay, in short, this DAA instructions will adjust the numbers. Okay, adjust the numbers. Which number? Our BCD, when the result falls into the invalid result. Okay, and I think we can wrap up here.